It might be surprising to know that in electric trains, the power collected from the overhead lines ends up in the grounding cable of the track after flowing through the wheels. Three-phase power conversion, regenerative braking, and zigzag overhead lines. All these make electric train technology quite unique. Let's understand all the engineering secrets behind the electric train, starting from the simplest design possible. The simplest version of an electric train is shown here. Here, a single sliding wire collects electric power from the overhead lines. This power is fed to a single-phase induction motor. The induction motor's rotor is connected with the wheels. To complete the circuit, the induction motor's other terminal is grounded. This grounding connection is possible because the wire is first connected to the wheels through an axle brush. The wheel is always in contact with the track, and the track is grounded, as shown. You can see how the current from the OHL flows to the ground. It first passes through the induction motor, then the axle brushes, then the wheels, and finally to the track and ground. When the current passes through, the induction motor's rotor spins, along with the wheels. However, a spinning wheel will move forward, which means the next grounding circuit should be available at a very short distance from the previous one. Now, let's look at some axle brush details. The axle brushes are fitted to the rotating wheel, and the current is transferred to the wheels through these carbon brushes, which slip over the disc attached to the wheel axle. Again, this is the simplest version of an electric train. Now, let's improve this design and make our train more functional. The voltage used in the overhead line is 25 kilovolt, which is a huge voltage. Motors require much less voltage to run. For this reason, we need to feed it to a step-down transformer, which transforms the voltage to the desired level. The power supply from the overhead line initially passes through the transformer's primary, and here, the circuit is completed due to the grounding. Because of the transformer's action, the current will be induced in the secondary winding and reduced voltage power is fed to the motor. For high traction like the train, the motor should supply a high torque. Moreover, the torque curve should be uniform, even if the motor speed varies. Three-phase induction motors are the perfect choice to achieve high, uniform torque requirements. Stretching three-phase wire to power this motor is not a good idea, as it's highly uneconomical. That's why a rectifier and inverter is used to convert the single-phase supply to the three-phase supply. A rectifier converts the single-phase AC power into DC power, and then the inverter converts the DC power into three-phase AC power. Now this engine is ready to run over the track. We can increase the torque output further if we add a transmission system with some gear ratio between the motor shaft and the wheel axle. At this point, the engine we just made seems perfect. However, if we make a complete train by connecting several coaches to this engine, it becomes quite clear that the single motor engine we developed doesn't have sufficient power to pull all these coaches. So, let's add more motor wheel pairs to make the engine more powerful. An engine bogie is constructed with three-phase induction motors, obviously to drive 3 pairs of wheels. In an engine, generally 2 such engine bogies are used. In this complete engine, you can see how the transformer and rectifiers are positioned. So far in this video, we've shown how we transfer power to the train using a single hanging wire. However, this method is not practical. Sometimes it is not possible to keep the distance between the train and overhead line the same, which means for proper power collection, a height-varying mechanism should be used. Pantographs accomplish this task. A modern pantograph looks like this. You can see that based on the pressure of a pneumatic system, the pantograph can adjust its height. If you observe carefully, you can see that during this height adjustment, the current collector remains horizontal. The current collector has to be perfectly horizontal. Otherwise, power transmission will be in trouble. We hope from this animation you can understand why the current collector always remains horizontal. For more details of it, please watch our detailed video about the pantograph. Now, let's see the pantograph in action. If for some reason the pantograph loses its connection with the wire, the train will continue its free run for a few kilometers due to its high momentum. Have you ever wondered why the overhead line stretches in a zigzag manner? This arrangement ensures that the pantograph's collector head doesn't touch the overhead wire at a constant point of contact. Due to this arrangement, the wear and tear is minimized. We can control the speed by changing the induction motor power supply's frequency. This is accomplished by the rectifier and an inverter. The driver sets the lever onto a different notch to change the frequency and hence the motor's speed accordingly. The most important aspect for the train after acceleration is stopping. How is this accomplished? Should we directly turn off the induction motors? If so, the train will keep on running over the tracks for several kilometers until it comes to a dead stop. Another idea is that we could apply electrical braking. In a normal induction motor, the rotor speed is lower than the speed of RMF. However, by lowering the supply frequency, we can reverse this condition. Interestingly, when RMF speed is lower than the rotor speed, the direction of induced current in the rotor bars reverses. This makes the induced torque on the rotor in the opposite direction. This is a perfect brake, a brake without metal-to-metal contact. During this phase, the motor runs a generating mode. However, this braking method can't stop the train dead in its tracks because regenerative braking doesn't work at low speed, which means it can slow the train down. But after that, you have to apply the pneumatic brakes to stop the train completely. This is a different kind of mechanical brake. Here, the spring force and compressed air forces are acting on the piston in the opposite directions. The interesting thing is that when the driver releases the air from the cylinder, the stretch spring pulls the piston towards the wheel and the brake gets applied. This brake system also provides security in the case of air leakage or broken compressor. The brake gets applied automatically as pressure releases. The pneumatic braking system is fitted under every coach for each wheel pair. Now, let's see how the power is supplied to each of the coaches. One way to supply the power supply for each coach's utilities is by self-generation. An alternator is mounted under the coach frame and driven by a cardan shaft, which is driven by a gearbox mounted on the axle. Output is rectified and charges a 110-volt DC battery, creating a continuous power supply to coaches. But this self-generating method is not efficient as it produces very fluctuating output power. So the most common way to supply power to the coaches is head-on generation. In this method, an extra winding is added up in the locomotive transformer, which supplies the power to all the coaches. Thank you for watching the video. See you next time.